We see incredible things AI can do every day, playing these really complex games, recognizing faces in our photos, even writing
Mm.
poetry or code now. It can feel almost like magic sometimes.
It really can seem that way.
But if you sort of peel back the curtain,
Hmm.
how do these systems actually work? What are the real foundational ideas, the bedrock principles that make all this capability possible?
That's a great question. And it's less magic and much more about rigorous engineering. It's built on some pretty deep theoretical roots.
Okay.
It's fundamentally about creating systems that can perceive the world around them, reason about what that perception means, learn from their experiences, and then act effectively based on all that. Those are really the essential building blocks,
Yeah.
the theoretical ground floor of artificial intelligence as a field.
And that's exactly what we're aiming for in this deep dive. We're going to spend our time today unpacking some of those absolute core concepts,
Yeah.
looking at the nuts and bolts of what it means to create what AI researchers call intelligent agents.
Right, agents.
We're drawing directly from some fascinating excerpts from a really fundamental text in artificial intelligence. So we're essentially getting a peek at the foundational principles behind how these AI systems interact with their environment, how they process information, learn, and make decisions.
Think of it like trying to understand the basic physics and engineering before you just stand there in awe of some incredibly complex machine. We'll explore what defines a rational agent, how it represents its knowledge, how it grapples with uncertainty, which is everywhere in the real world, and how it acquires skills and information from data and its sensors.
All right, let's really dig into this then. Starting with that core idea of an agent. What makes it, what makes it rational? What's the sort of fundamental goal that drives these systems to act autonomously?
Okay, so at its most basic level, a rational agent is conceptualized as a system, and it's designed with a really clear objective to act in a way that's expected to achieve the best possible outcome in whatever situation it's in.
The best outcome.
Yeah. And if the situation isn't perfectly certain, which, let's face it, is usually the case in the real world,
Right.
then the rational agent aims for the action that yields the best expected outcome. It has to weigh the probabilities and the values of different possibilities. This whole pursuit of optimal action. That's a central thread running through, well, a lot of AI design.
So it's maybe less about how it does things, the
Hmm.
specific steps, and more about the result maximizing some kind of measure of success or utility.
Exactly. The focus is squarely on the logical consequence of its actions, given what it knows and what it perceives. Now, tied very, very closely to this is the concept of autonomy,
Mhm. Autonomy.
which the source really delves into. And this isn't just about acting, it's about acting independently and adaptively.
Autonomy feels super important for any AI that has to operate outside, a controlled lab environment. What's the definition the source gives for that?
The definition is quite precise and, I think, revealing. It says an agent lacks autonomy to the extent that its actions are solely dictated by the designer's prior knowledge, rather than being influenced or determined by its own learning and experience. The things it gathers through its sensors, its percepts.
Percepts meaning what it sees, hears, senses.
Exactly. So the ideal goal, the aspiration for a truly rational agent, is that it should be autonomous. It should be constantly learning from what it perceives to improve its ability to handle situations, especially those situations where its initial built-in knowledge might be partial or incomplete or maybe even just plain wrong.
That makes a lot of intuitive sense. I mean, no human designer, however brilliant, could possibly anticipate every single nuance, every challenge an AI might face out in the real world. Think about a self-driving car hitting some totally unpredictable road hazard or...
Or a recommendation system dealing with your taste suddenly changing.
Yeah, exactly.
Precisely. You can try to program for a huge number of scenarios, but you'll inevitably miss some. And this is where learning from experience becomes absolutely crucial. The source uses a simple, but I think effective, example. A vacuum cleaning agent, just navigating a house. If this agent is designed to actually learn where and when dirt typically appears, maybe it notices the kitchen floor gets dirty after meals or the entryway gets muddy after people come inside.
Right, it builds a pattern.
It builds a pattern. It can then develop a strategy to clean those areas more frequently or perhaps at specific times of day.
Instead of just blindly following some fixed, pre-programmed path,
Yeah,
or only reacting when it literally runs over dirt.
exactly that. An agent that learns from the pattern of dirt accumulation will be significantly more efficient, more effective over time than one that just traverses a predefined route or only reacts when a sensor is triggered right underneath it. Learning allows it to build expectations and plan proactively.
So autonomy is fundamentally linked to the agent's ability to learn and adapt based on its own interaction with the environment. It's not just acting, it's about becoming less reliant on its creator over time.
That's a key takeaway, absolutely. The aspiration, the long-term goal, is that after sufficient experience interacting with its environment, a rational agent's behavior can become effectively independent of the specific prior knowledge that was originally hard-coded by the designer. It should have built its own internal model, its own strategy based on real-world data.
But hang on, is complete autonomy always the starting point? It feels like you'd need some basic capability just to begin learning, right? To not just, crash immediately.
Right. That's the practical reality. Complete autonomy from the very beginning isn't typically required or maybe even desirable. Designers usually provide agents with some initial knowledge. Think of it like the built-in reflexes that animals are born with.
Oh, like instincts.
Kind of like instincts, yeah. These initial capabilities allow the agent to function at a basic level, to survive its initial encounters with the environment, and basically operate long enough to actually start the process of learning. It's a starting point, it's not the final state.
So you give it some foundational knowledge, almost like instinct, but the real long-term success comes from its ability to build on that through its own experience.
Precisely. And this ability to learn, to incorporate experience, it's incredibly powerful. It's the reason a single underlying agent design can potentially succeed and perform well in a vast variety of environments, even if those environments are significantly different from what the designer originally built it for. It's really the path to true adaptability through interaction.
That adaptability through learning.
Yeah.
Yeah, that feels like a core characteristic of the most impressive AI systems we see today.
When you think about the AI agents you interact with daily, maybe it's your phone's assistant or a streaming services recommendation engine, even those customer service chatbots, where do you see this balance playing out? Can you tell when they're just following a script, based on built-in rules, versus when they seem to be adapting, learning from your specific interactions, maybe your preferences, or even the mistakes you make? It's often a dynamic blend, isn't it? Many core functionalities are indeed based on pre-programmed knowledge or rules. That's the foundation. But the personalization, the way it seems to anticipate your next question sometimes, the refining of recommendations based on what you actually watch or buy, the improvement in understanding your particular voice or accent over time, those are all pretty clear examples of the agent leveraging learning. It's achieving a greater degree of effective autonomy in relation to you specifically, and that makes the interaction more rational and more effective from its perspective.
Fascinating. Okay, so an agent perceives the world, it starts gathering information, and it aims for rational autonomous action by learning. But how does it actually use that information? How does it process those perceptions and its built-in knowledge to figure out what to do next? This seems to bring us to how agents reason and represent what they know.
Exactly. This moves us squarely into the realm of logical agents and knowledge representation. And a classic example, one used all the time to illustrate how an agent can use perception and logic to infer information about its environment, is the Wumpus world.
The Wumpus world. Yes, I remember that from AI text. It's sort of a staple. Tell us about that scenario.
It is a staple. It's a simple, grid-based virtual world, often depicted as like a cave system. The agent navigates square by square, trying to achieve a goal, usually finding some gold while avoiding dangers.
Dangers
Like the Wumpus, which is this creature that emits a terrible stench in the squares directly adjacent to it, and also bottomless pits, which generate a breeze in the squares adjacent to them.
Okay, so local smells and breezes signal nearby dangers.
Exactly. The agent has basic sensors. It can perceive a stench, a breeze, or glitter, if it's in the square with the gold, but only in the square it currently occupies. It also knows its location on the grid and can keep track of where it's already been.
So it has very limited, very local information, and it has to use that to somehow infer the global properties of the cave and plan its moves safely.
Precisely. The source walks through a specific illustrative scenario. Imagine the agent starts in square 1-1, which it knows is safe. Okay. It moves to an adjacent square, let's say 12-2, and its sensors detect a stench.
Uh-oh.
Wumpus nearby. Right. It knows from its built-in rules that a stench means a wumpus is in an adjacent square. So the adjacent squares to 12-2 are 11-1, 1-3, and 2-2. Now, since it knows 11-1 is safe, it just came from there, the wumpus must be either in 1-3 or in 2-2. It doesn't know which one yet, just that one of them holds the wumpus.
Okay, so it's narrowed down the possibilities for the wumpus.
Exactly. Now, let's say it moves back to 11-1 maybe because Wovball had that danger signal, and then it tries another adjacent square, say 2-1. In 2-1, its sensors detect a breeze.
Okay, so a pit nearby now.
Right. Again, it knows a breeze indicates a pit in an adjacent square. The squares adjacent to 2, 1 are 11, 1, 2, 2, and 3, 1. It knows 11, 1 is safe. So the pit must be either in 2, 1, 2 or 3, 1.
So now it has possible locations for the Wumpus 1 through 2, 2, and possible locations for a pit 2, 2 or 3, 1. How does it combine this information? Where does the reasoning come in?
This is where the logical inference really happens using its knowledge base. So, recap. From the stench at 1, 2, the Wumpus is in 1 value 3 or R2 arrow. From the breeze at 2, 1, a pit is in 2 or 2 or R3, 1. Now, importantly, the agent also knows where it hasn't sensed things. It was in true over 2, and it only sensed a stench. It did not sense a breeze there.
Ah, okay. The absence of a signal is also information. That's crucial.
It's absolutely crucial information because it knows there is no pit in 12 of 2, and the breeze it sensed back in 2 and 1 must come from an adjacent pit. Well, the only remaining adjacent square to 2 of 1 that could possibly contain the pit is 2 over 2.
Got it.
Therefore, it can logically deduce there is a pit in 2 over 2 with certainty.
Wow. Okay, so just from a stench in one place and a breeze in another, plus knowing where it didn't sense something, it pinpointed the location of a pit.
Precisely, and it can take it further. Based on the original stench at 22, which told it the Wumpus was in 1-3RR-202, combined with now knowing there's definitely a pit in 2 over 2.
And the Wumpus can't be in 2 over 2. Wait, or could it? Could a square have both?
Ah, good question. The basic Wumpus world usually assumes they're distinct, but the logic allows for possibilities. The key inference here is about safety for movement. It knows 2 Bella 2 is dangerous. Pit. It still suspects 1 Ben 3 might have the Wumpus, and 3 1 might have a pit. The agent continues this process using logic to classify squares. Definitely safe, definitely dangerous, pit or Wumpus identified, or potentially dangerous. And this guides its path, helping it explore safely, find the gold, or map out the dangers.
This simple scenario really does highlight how an AI agent can build up a picture of its world and make these logical deductions based on really limited sensor data and a set of rules.
It's the essence of knowledge representation and logical inference in AI. The agent maintains an internal model, its knowledge base, and it applies logical rules to derive new facts from existing ones, and importantly, from its perceptions.
And this all relies heavily on the rules of logic itself. The source discusses a property of standard logics called monotonicity. What does that term mean in this context? Is it important?
It's a fundamental property, yes. Monotonicity applies to many standard formal logics, including the kind we typically use in AI reasoning systems, like the one navigating the Wumpus world. It essentially means that if you add new sentences or facts to your knowledge base, it can only increase the set of conclusions you can logically derive or keep it the same. You can never lose or invalidate a conclusion that was already entailed, meaning logically supported, by your original knowledge base.
Okay, so let me see as I get this. If I use the rules to figure out, say, there is no pit in square 12 over 2, and then later I learn some completely new fact, like, I don't know, the Wumpus is actually gold-plated, that new fact won't suddenly make my previous conclusion, no pit in 12.2, false.
Exactly. As long as your reasoning steps for concluding no pit in 12.2 relied only on information that was already in your original knowledge base, that conclusion remains valid, no matter what new, consistent information you add later. Inference rules in these monotonic logics are applied based purely on whether their premises are met by the current knowledge. It doesn't matter what else is in the database.
That feels very rigid. Is that always how humans reason? We seem to change our minds all the time when we learn new things.
That's a really good point, and the source actually hints at this by briefly mentioning non-monotonic logics. These are different logical systems where adding new information can actually invalidate previous conclusions. And this reflects a common aspect of human reasoning, right? We often draw conclusions based on incomplete information, sort of default assumptions, and then we retract them when new evidence comes along that contradicts them. Like, you might conclude, my friend is home because you see their car in the driveway.
Right. Seems reasonable.
But then you get a text message saying they're actually out of town. Your initial conclusion is invalidated by the new information. Standard formal logic is monotonic. Capturing that kind of default reasoning and belief revision requires these non-monotonic systems, which are generally more complex to build and reason with formally.
So it sounds like there's a trade-off. Standard logic gives you certainty in your deductions, which is good. But non-monotonic logic might be more flexible, maybe closer to how humans actually reason, but is harder to manage computationally.
Precisely. It highlights a fundamental challenge in building AI. You have to choose the right formalism, the right way to represent knowledge and perform inference, depending on whether you absolutely need certainty or if you need more flexible adaptability.
Okay, so agents use logic, they use inference, they build up this knowledge base. How do they actually structure and represent all that information they gather and are given? How is it stored?
Right, knowledge representation. The source touches on a few different approaches. One very powerful language is first-order logic. It lets
Hmm.
you represent objects, properties of objects, and also relationships between objects. It mentions the syntax, basically, how the statements are written down. The standard form is usually prefix notation, like predicate, object 1, object 2.
Okay.
But we, as humans, are often more used to infix notation, especially in math, like object 1 plus object 2.
Yeah, like writing 2 plus 2 instead of what? Plus 2, 2.
Exactly. And in logic notation, using terms like m plus n instead of something like sum n is often referred to as syntactic sugar.
Syntactic sugar, I like that term. Makes it sound less intimidating somehow.
It does, doesn't it? It's essentially an extension or an abbreviation to the standard syntax that just makes the logic statements much easier for humans to read, write, and understand. It doesn't actually change the fundamental meaning or the expressive power of the logic underneath. It's just a notational convenience. Any sentence written with syntactic sugar can theoretically be converted back into the standard prefix form.
So it's really about making the internal representation easier for the human designers and analysts to work with without changing the underlying logic the AI itself is using.
Precisely. Now, representing simple facts and relationships is one thing, but what about representing concepts that aren't distinct, countable objects? The source brings up the interesting challenge of representing stuff, or what linguists call mass nouns within these knowledge structures, or ontologies.
Mass nouns. You mean like water, butter, air, energy. Things you can't easily count like 1, 2, 3 chairs.
Yes, exactly those. In knowledge representation, you might need to deal with specific instances, like the lump of butter currently on the table. The approach described in the source is to represent these specific physical manifestations, these lumps, as individual objects. Let's call it lump off butter 3.
Okay, makes sense.
But then you need to relate this specific lump back to the general concept of butter.
So you'd create a category maybe called butter.
Exactly. And the category butter would include these specific lumps like lump off butter 3. But here's the crucial caveat that the source highlights. For mass nouns, there's a specific property. Any part of an object that falls under that mass noun category is also considered to be that mass noun.
Ah, right. If I take a piece off that lump of butter, that piece is still butter.
Precisely. Which is different from count nouns, right? A part of a chair isn't usually considered a chair itself. A leg isn't a chair.
That's a subtle but really important distinction. An AI knowledge system needs to handle that correctly if it's going to reason accurately about the physical world.
It absolutely is. Getting these fundamental distinctions right in how knowledge is structured is critical. The source also briefly mentions semantic networks. These are more like graph-like structures where concepts are nodes and relationships are the links or edges between them. And it points out a potential pitfall regarding the links that are attached to categories.
What's the issue there? Sounds straightforward.
Well, you have to be really careful to distinguish between links that describe the category itself versus links that describe the members of that category. The source uses some technical terms like unboxed and singly boxed links to represent this distinction. But the core idea is this. You can't just assume that if a link connects to a category node, it automatically applies to every single instance or member of that category.
Okay, give me an example.
Sure. Imagine you have a birds category and a can fly property. You might link them. But you need a specific type of link to say, typically members of the birds category can fly, which allows for exceptions like penguins or ostriches. That's different from a link meaning every single individual object currently in the birds category can fly, which is clearly false. Making the wrong assumption about the meaning of the link type can lead the AI to make incorrect inferences.
Ah, I see. So the exact nature and the scope of the relationship represented by that link are crucial to prevent the AI from making these overly broad or just plain false generalizations.
Precisely. It's all about building a knowledge base where the relationships are defined with enough precision to support accurate reasoning. Think about that shopping compatibility example mentioned in the source, figuring out which camera battery works with which specific camera model. Building that knowledge base requires precisely representing camera models, battery types, and that specific is compatible with relationship. You have to ensure the AI doesn't incorrectly conclude that any battery works with any camera just because they both happen to fall under a broader electronics category.
Yeah, that connects this kind of abstract idea of knowledge representation directly to practical AI applications that we use every day.
It really does. It's the hidden structure, the careful definitions that allow these systems to answer our questions, make sensible recommendations, or verify compatibility accurately.
Okay, so agents perceive, they reason using logic and structured knowledge. But the real world, unlike the nice, clean Wumpus world grid, is rarely perfectly certain. Things are messy. How do rational agents handle all that uncertainty and make decisions when they don't know everything for sure?
This is where we really need to move beyond pure logic and into the realm of probabilistic methods. It becomes essential. The source introduces Bayesian networks as a key tool for reasoning under uncertainty. These are basically graphical models that represent dependencies between different variables using probabilities.
So instead of a definite, this square is safe, it might be more like, this square is likely safe, maybe with an 85% probability.
Exactly. It's all about quantifying belief, putting numbers on how sure we are, and then using the rules of probability theory to update those beliefs as new evidence comes in. Within this probabilistic framework, a really critical question for any rational agent becomes, is it actually worth expending resources, maybe time, computation, or even risking negative consequences to get more information before I take an action? This leads to the concept of the value of
The
information.
value of information, like how much is potentially knowing something new actually worth to my decision-making process right now?
Precisely that. The source illustrates this nicely with a diagram showing three sort of generic scenarios. They're based on the potential utility or outcome of different actions depending on some unknown factor. Let's walk through them. Casey, imagine you have two options, action 1 and action 2. Based on your current knowledge and the probabilities you've assigned, action 1 already has a significantly higher expected utility.
Meaning, on average, it's likely to turn out better.
Right. If you average out all the possible outcomes of taking action 1 weighted by their probabilities, that average value is clearly better than the average value you'd get from action 2. In this scenario, even if you got more information, it's pretty unlikely to change the fact that action 1 is the best choice. So going out and getting more information probably has low value here.
Because the best path forward is already pretty obvious, given what you currently know. Makes sense.
Right. Now consider case B. Here, the expected utilities of action 1 and action 2 are very, very close based on your current information. You're essentially unsure which one is better. And furthermore, there's high uncertainty. The probability distributions for the outcomes of both actions are quite spread out. They could lead to very good or very bad results.
Okay, so it's a toss-up, and the stakes feel high.
Exactly. In this case, obtaining new information, let's call it evidence E, could be absolutely crucial. This new evidence is likely to significantly shift those probability distributions, maybe showing that action 1 is now clearly much better, or maybe action 2 is. It clarifies the choice. So here, the value of information is high because it's likely to resolve the uncertainty in a way that leads you to choose a much better action than you might have picked otherwise.
The information acts like a critical tiebreaker, where the potential difference in outcome is significant.
Exactly. It clarifies a previously murky choice that had a significant potential upside or downside. Okay, finally, case C. Similar to case B, the expected values of action 1 and action 2 might be close, again making the choice unclear. However, in this particular case, the difference in potential utility between the best possible outcome and the worst possible outcome among your choices is relatively small.
So even if you figure out which is slightly better, it doesn't make a huge difference.
Right. Even if new information clearly shows that, say, action 1 is slightly better than action 2, the actual gain in expected utility you get from making that optimal choice instead of the slightly suboptimal one is pretty minor. The options are just not that different in terms of their consequences.
So the value of information isn't just about reducing uncertainty in general. It's about whether reducing that uncertainty is likely to significantly improve your eventual outcome.
Absolutely. Information has high value when it helps you make a decision where the different choices have significantly different potential outcomes, and your current knowledge leaves you really unsure which choice is best. If the options are already clearly separated in value, or if the difference between the best and worst outcome among the options is small anyway, then the information is less valuable. It's not worth the cost or effort to get it. The source mentions sort of technically calculating conditional distributions like PM1N, the probability of observing measurement M1 given the world is in state N as part of figuring out how new information changes your beliefs, which is fundamental to calculating its value.
And the source also touches briefly on how we try to quantify value and risk more broadly, bringing up things like assessing personal utility for money or that concept of a micromort.
Yes, those are interesting examples of how AI researchers and decision theorists in general try to put numerical values on subjective concepts, like how much we value money. Often, the value isn't strictly linear, right?
Yeah.
Gaining $100 when you only have $100 feels very different than gaining $100 when you already have $100 million.
Straight.
Or quantifying risk, a micromort is defined as a unit of risk equivalent to a 1 in a million chance of death. It sounds morbid, but it's a way to try and normalize different risks, like the risk of traveling by plane versus driving a car, so they can be compared and potentially incorporated into rational decision-making processes. That includes the decisions made by AI agents, especially those operating in high-stakes environments like autonomous vehicles or medical diagnosis.
That is a very direct, almost stark way to quantify risk.
It is, but it illustrates the need for these formal methods when you're designing agents that have to make decisions involving complex trade-offs between potential gains and potential harms, especially when those decisions unfold over extended periods in uncertain environments. And this leads us naturally to thinking about decision-making over time, particularly in dynamic or what are called stochastic environments.
Stochastic meaning random or unpredictable to some degree.
Exactly. Where the outcome of an action isn't guaranteed, but depends on probability, like rolling dice or dealing with unpredictable traffic patterns or the stock market.
So like navigating a complex changing world where things aren't perfectly predictable? Most of the world, basically.
Exactly. In such environments, an agent needs more than just a single decision. It needs a policy. A policy, often denoted by the Greek letter pi, is essentially a function. It specifies the action the agent should take in every possible state it could find itself in.
So it's like a complete contingency plan. For any situation it encounters, the policy tells it what to do.
Yes, that's a good way to think about it. However, because the environment is stochastic, if the agent starts in the same state and follows the same policy multiple times, it might actually end up following different sequences of states and actions each time. It generates different environment histories because the outcomes of its actions have that element of randomness.
Right, the dice roll differently each time,
Yeah.
even if you use the same throwing strategy. So the quality of the policy isn't just about one specific sequence of events, but about all the possible sequences it could generate.
Correct. The quality of a policy is measured by the expected utility of all the possible histories it can generate. You have to calculate the utility, the total value of each possible sequence of states and rewards that could result from following the policy. Then you determine the probability of following that specific sequence under the given policy in that stochastic environment. And finally, you average all those sequence utilities weighted by their probabilities.
Okay, that sounds computationally intensive.
It can be very intensive. But the goal for the rational agent is to find the optimal policy. That's the policy that yields the highest possible expected utility when averaged over all possible environment histories it could produce.
So that's the ultimate aim. Finding the strategy, the complete plan, that maximizes the agent's long-term expected success in an unpredictable world. When my GPS app reroutes me based on traffic predictions, or a robotic arm adjusts its grip based on slight variations in sensor feedback, or an investment algorithm rebalances a portfolio based on market volatility, they're all, in a sense, trying to operate based on some calculation of an optimal policy given uncertain, changing information.
They are certainly aiming to. It's about projecting into the future, considering all the potential outcomes and their likelihoods across many steps, and then choosing the actions now that maximize the overall expected value accumulated over time. It's a complex planning problem under uncertainty.
Okay, wow. We've covered agents being rational, becoming autonomous through learning, reasoning with logic, representing knowledge carefully, and making decisions under uncertainty using probability. But all of this capability fundamentally relies on the agent getting information from the world in the first place. How do these systems actually perceive their environment and then learn from the data they collect?
That brings us to the absolutely crucial areas of perception and learning from examples. Perception basically is the process by which an agent uses its sensors to acquire raw information about its environment. And then, importantly, it has to interpret that raw data to form some kind of meaningful understanding.
Like our own senses, eyes, ears, sense of touch.
Exactly. Those are our primary human sensor modalities. Artificial agents have counterparts to those, but often they have entirely different ones as well. The source lists a whole variety. Vision, obviously using cameras, hearing, using microphones, touch, using tactile sensors, but also modalities we don't possess directly, like radio signal strength, infrared sensors for heat signatures, GPS coordinates for location, and general wireless signals. Some systems even use active sensing.
Active sensing.
Yeah, where they actually send out a signal like radar waves or sonar pings and then interpret the reflection that comes back to understand their surroundings. Bats and dolphins do this naturally.
So AI perception isn't limited to just mimicking human senses. It can go way beyond.
Not at all. It extends far beyond human capabilities in many ways. However, the source material we're looking at focuses quite a bit on vision because it's such a key and complex perception modality for many applications.
Okay, so how does an AI system see? What are the basics of how an image gets formed from the AI's perspective? Is it just pixels?
Fundamentally, yes, a digital image is a grid of pixels. Each pixel has a value representing its brightness, or, in color images, its color components. At the most basic level, the brightness value of a pixel in the image is related to the amount of light that reflected off the corresponding patch of surface in the 3D scene and hit the sensor. The source often models this as a roughly linear relationship. A brighter surface in the scene generally means a brighter pixel in the image.
But real-world images are much more complicated than that, right? You have shadows, shiny spots, different textures. How does AI deal with all that visual complexity?
Those are precisely the illumination effects the source discusses, and they make vision hard. You often see examples like trying to understand an image of a simple object like a spoon. You'll have specularities, which are those really bright, almost mirror-like reflections you get off shiny surfaces, polished metal, wet roads, that kind of thing.
Right, the glint.
Exactly, the glint. Then you have cast shadows, where one object completely blocks the light source from hitting another surface, creating a dark area. And very importantly, you have diffuse reflection. This is how light bounces off matte or non-shiny surfaces. The brightness of a surface due to diffuse reflection isn't usually dependent on your viewing angle, but it does vary depending on the orientation of the surface relative to the light source. A surface patch facing directly towards the light will be brighter than one that's angled away from it.
So an AI needs to interpret all these different patterns of light and shadow, not just as brightness values, but as clues to understand the underlying shapes and materials of the objects in the scene.
Yes, these are all cues. But often, the raw pixel brightness values themselves aren't the most informative or stable features for higher-level tasks like recognizing objects. The source talks about the importance of creating more robust features from the image. For instance, orientation features.
Orientation features.
Yeah, features that capture the direction of brightness changes, like edges or lines. These are often invariant or less sensitive to the overall image brightness. An edge where brightness changes sharply will still look like an edge. It will still have the same orientation, whether the whole image is a bit dark or a bit light.
Okay, so focusing on features that are stable, despite variations in lighting, makes sense. That seems useful. But doesn't focusing just on the orientation mean you lose information about how strong that edge is? You know, the contrast, a faint edge versus a really sharp one.
That's a really valid concern. And the source explains a technique, calls it a trick, actually, to recover some of that contrast information while still primarily using orientation features. The idea is you can weight the importance of an orientation feature based on the gradient magnitude in that local area of the image.
Gradient magnitude. Okay, what does that mean conceptually? Like how steep the change is?
Exactly. The gradient magnitude, you might see it written like Age of Text, measures how quickly and steeply the image brightness is changing at a particular pixel or in a small region. A large gradient magnitude means there's a sharp change in brightness, like a strong, clear edge. A small magnitude means the brightness is changing very slowly or not at all, like in a smooth, uniform area.
Okay.
So by weighting the orientation features by the gradient magnitude in, say, a local cell of the image, the system gives more importance to orientations that correspond to strong, distinct edges and less importance to maybe noisy variations or very weak texture details. This helps the AI focus on the significant structural lines in the image.
Huh, that's clever. So you use the strength of the brightness change to highlight the most important directional features in that area.
It's a key technique in computer vision, yeah. Once you have features like these, the goal is often scene reconstruction, trying to understand the 3D layout of the world from the 2D image or images. And the source makes a really important point here. It notes that there isn't currently a single, unified, elegant theory for how to do this perfectly, which really highlights just how difficult this problem is.
So there's no one magic bullet.
Yeah.
Multiple different approaches and cues have to be used together.
Exactly. The source lists several important visual cues that AI systems leverage to piece together the 3D scene. There's motion, how objects or the camera itself move over time. There's binocular stereopsis, using two cameras slightly apart, just like our two eyes, to perceive depth. There's using multiple views images taken from different angles or at different times. There's texture, how the appearance of patterns changes with distance and angle. There's shading, how light and shadow fall on curved surfaces, giving clues about their shape. There's contour, the outlines of objects. And also recognizing familiar objects using prior knowledge about what certain objects typically look like and their likely shapes.
Can you maybe give us a bit more detail on one or two of those techniques? How do they work?
Sure, let's take triangulation. This is a fundamental technique used often with multiple views or binocular stereo. If you can reliably identify the same physical point in the real-world scene in two or more images taken from different known camera positions.
Like seeing the same corner of a building in two photos.
Exactly. Then you can use basic geometry, essentially drawing triangles in 3D space with the cameras and the point to calculate the precise 3D coordinates of that point in the real world.
Ah, okay. It's like surveying, but done with cameras.
Yes, it's the same underlying geometric principle. Another approach mentioned uses background knowledge in a probabilistic way. If the AI has a model of the probability of different possible scenes occurring, call it P, and it also has a model of how images are formed given a particular scene, P image scene, which involves optics and lighting, then it can use Bayes' rule to infer the most probable scene given the actual image it observed, calculate P scene image. It's combining its prior expectations about the world with the specific evidence from the image it just saw.
Combining what it sort of expects to see with what it actually sees. That makes sense.
Right. The source also discusses texture cues in a bit more detail. The appearance of textures in an image changes predictably with distance and the angle of the surface they're on. For example, the scaling of a texture pattern is generally inversely proportional to its distance. Textures on faraway surfaces look smaller and denser in the image.
Okay.
And foreshortening, which depends on the angle of the surface relative to the camera, often related to cause, makes textures look compressed or squashed on surfaces that are slanted away from you. Algorithms try to use these systematic variations in texture appearance to infer the orientation and distance of surfaces. But the source does note that using texture cues alone isn't always as reliable or generally accurate as using information derived from multiple views, like triangulation.
So texture cues are useful, they provide information, but maybe they're less robust than triangulation or stereo vision. What about identifying what the perceived objects actually are? Not just where they are, but what they are.
Right, that's object recognition. And this is crucial for so many AI tasks, both for an agent to physically interact with the world, like knowing how to grasp a mug versus a box, and simply to understand what's in the scene, identifying a person, a car, a stop sign. Recognizing objects and even specific parts of objects, like arms, legs, heads on a person, is really challenging because they can look incredibly different depending on the viewing angle, the lighting conditions, and whether they are partially hidden or occluded. Small parts, like maybe forearms or shins in a full-body image of a person, can be particularly hard to detect reliably just from their local pixel information.
Yeah, I could see that. How do AI systems try to overcome that variability and difficulty? What are the strategies?
A key strategy highlighted is using structural information. Knowing how the different parts of an object typically relate to each other geometrically can be incredibly powerful.
Like, knowing an arm is usually attached to a torso.
Exactly. If an AI system can reliably detect a larger, more distinct part, like maybe the torso of a person, it then knows roughly where to look for the smaller, harder to detect parts, like the arms or the shoulders. It knows their likely relative positions and orientations. This structural context helps constrain the search space and significantly improves accuracy, especially in noisy images or when parts are partially obscured. The source mentions using those histogram methods we talked about earlier, pooling evidence from orientation features in a region to find larger structures, like the overall boundaries of a pedestrian, even if the individual pixels or small edges within that boundary are noisy or unclear.
So it uses the knowledge of the overall shape and the relationships between the parts to boost its ability to find the individual pieces. That makes a lot of sense. It's like context.
It's absolutely using context, yes. It's a critical element in making computer vision systems more robust. And just briefly, on robotic perception specifically, the source mentions some typical tasks like calculating the range, the distance, and the bearing, the direction, to objects using sensors like sonar or LiDAR. And it also mentions the practical need to model sensor noise. Real sensors aren't perfect. Often, for mathematical convenience, this noise is assumed to follow a Gaussian distribution, that familiar bell curve shape. And arrays of range sensors, which are common in LiDAR units on self-driving cars, for example, produce a whole vector of range readings from multiple beams simultaneously, giving the robot a kind of depth map of its immediate surroundings.
So whether it's interpreting complex light patterns in images, calculating distances with LiDAR beams, or maybe processing audio signals, the core task of perception is always about converting that raw, messy sensor data into some kind of structured, meaningful information features, 3D points, object identities that the agent's reasoning and decision-making systems can actually use. It sounds incredibly complex, honestly.
It really is. And the fact, as the source points out, that there isn't one single elegant, unified theory for something as seemingly fundamental as 3D scene reconstruction from images, that really underscores the inherent difficulty and the ongoing research challenges in getting AI to perceive the world as flexibly and robustly as humans seem to do, almost effortlessly.
Absolutely. And speaking of complex interpretation, from understanding visual data, let's shift gears to something arguably even more nuanced: human language. How do AI agents even begin to understand and process natural language?
Right. This brings us to the fascinating field of natural language processing, or NLP. It's the branch of AI specifically dedicated to enabling computers to comprehend, interpret, generate, and generally work with human languages, whether that's written text or spoken language.
Okay, so where does an AI even start with language? Like, can it tell if it's hearing English or German or Japanese?
Yes, language identification is actually considered a relatively straightforward task in NLP today. Systems are remarkably accurate, often achieving well over 99% accuracy, even with fairly short pieces of text or snippets of audio. The main challenges really only arise with very, very closely related languages. The source mentions Swedish and Norwegian being confusable, for example, or with extremely short snippets where there just isn't much data.
Okay, but how do they do it? How do they figure out which language it is? What's the trick?
One common technique mentioned is building trigram character models for each language you want to identify.
Trigram character models.
Yeah, you analyze a vast amount of text for English, then for German, French, and so on. And for each language, you count how often different sequences of 3 consecutive characters appear. So you build up a statistical model of typical English trigrams. Things like the ing, ion, kua, including spaces, is important. Then, when you're presented with a new piece of text, the system analyzes the character trigrams it contains and uses statistical methods, like applying Bayes' rule, to determine which language model is most likely to have produced that particular sequence of characters. The source notes you typically need around 100,000 characters or so of training data per language to build reliable models this way.
Huh. So it's essentially sophisticated pattern matching, but at the level of tiny character sequences.
That's a pretty good way to think about it, yes. And this idea of statistical pattern matching is really foundational to many machine learning approaches in NLP. Often, messages or entire documents are represented for learning algorithms as sets of feature value pairs.
Okay, feature value pairs. What kinds of features are we talking about for language?
Well, the characters, or the character sequences, the engrams we just discussed, can be features. But more commonly, especially for tasks that go beyond just identifying the language, the features are the words themselves. A very simple, yet often remarkably effective model is the bag of words model.
The bag of words. Okay, that sounds exactly like you just toss all the words from a document into a bag and count them up.
That's precisely the intuition. In the bag of words model, the features are basically all the unique words from the entire vocabulary the system knows about. And the values associated with a specific text are simply how many times each word from that vocabulary appears in that text. The critical thing to understand is that this model completely ignores the order of the words and any grammatical structure of the sentence.
So the sentence, "the dog bites the man," would have the exact same bag of words representation as "the man bites the dog."
Exactly the same. Just counts for the appears twice, dog appears once, bites appears once, and man appears once. For relatively short texts, this results in very large feature vectors because the overall vocabulary can be huge, but most of the entries in the vector for any given short text will be 0. We call that sparse.
And this seemingly, well, simplistic approach actually works well in practice, just counting words and ignoring grammar.
That's one of the really key principles highlighted by the source, especially regarding statistical language systems. Often, the best practical approach is to design a model that makes effective use of the available data, even if the model itself seems linguistically simplistic or naive. Having massive amounts of training data can often compensate for the model's lack of deep sophistication regarding syntax or semantics.
Interesting. Where do we see this principle in action in real-world AI applications?
Information retrieval, the core technology behind search engines, is a prime example. Simple bag of words models or variations like TF-IDF, which weights words by importance, are highly effective for indexing massive collections of text documents like the entire web and quickly finding documents that are relevant to a user's search query, which is often just a few keywords. Now, these systems might be augmented by other techniques like the link analysis algorithms Google pioneered, PageRank, looking at how web pages link to each other, to further improve performance and ranking, especially on web data. But the core indexing and initial retrieval often relies heavily on these frequency-based bag of words type methods.
So when I type a few keywords into a search engine, a bag of words-like system is probably doing the heavy lifting behind the scenes to find documents that contain those words frequently.
Essentially, yes, that's a big part of it. Question answering systems can also leverage these information retrieval methods. For questions where the answer is likely stated explicitly somewhere within a large collection of texts, these systems can first retrieve potentially relevant passages using IR techniques and then apply more focused processing to extract or synthesize the actual answer. These systems often prioritize precision meaning, ensuring the answer they give is highly likely to be correct over recall meaning, finding every single possible place the answer might be mentioned in the text.
Okay, that makes sense for finding answers. What about pulling out specific pieces of structured information like names of people, dates, company names, locations, from just plain unstructured text like news articles?
Right, that's the task known as information extraction, or IE. This generally requires more sophisticated models than simple bag of words because now you do need to understand at least some limited syntax and semantics to identify specific types of entities, like people, organizations, locations, and often the relationships between them, like person X works for organization Y, or company A acquired company B.
So it needs more grammar.
It needs to recognize patterns that involve more than just word counts. These IE systems often use predefined templates to identify and structure the information they're looking for. The underlying technology can involve techniques like finite state automata, machines that recognize specific sequences, hidden Markov models, HMMs, or conditional random fields, CRFs. These are all types of models that are good at dealing with sequential information and learning complex patterns from annotated examples.
So IE uses more structured methods to find structure within unstructured text. It sounds more complex.
It generally is more complex than basic bag of words. But circling back to that key principle, while IE requires more sophistication for many common language tasks, the sheer power of having a massive amount of data to train even a simpler statistical model on can yield surprisingly excellent results. The source explicitly makes this point. When you're building statistical language systems, it's often better to devise a model that makes really good use of the data you actually have available, even if that model seems overly simplistic from a purely linguistic theory perspective.
That's a really important practical point about modern AI design, isn't it? The elegance of the model architecture matters, certainly, but maybe the quantity and quality of data it's trained on matters just as much, or even more sometimes.
Massively so. Data is often king. The source also briefly touches on the inherent complexities of handling formal language structure and grammar rules that AI systems would need to understand for truly deep language processing. It mentions things like case agreement, knowing the difference between subjective pronouns like I or he, and objective ones like me or him, and subject-verb agreement, making sure the verb form matches the subject, like he runs versus they run. It notes the difficulty, suggesting that even carefully designed rule sets can still overgenerate, meaning they might produce sentences that follow the rules but are still grammatically incorrect or nonsensical sometimes.
Right, highlighting that even seemingly simple grammar rules in English can have incredibly complex edge cases and interactions.
Exactly. And representing and processing those rules computationally in a robust way is non-trivial. The source also gives a quick nod to the historical context, acknowledging the decades of work in areas like statistical machine translation, mentioning key research groups involved, like those at IBM, ISI, Information Sciences Institute, and Google, and some prominent figures who made significant contributions to the field.
It's good to acknowledge the long history and the shoulders that today's systems stand on. So, okay, from figuring out which language you're even using to enabling powerful search capabilities based often on simple word counts, all the way to extracting structured facts from messy documents.
Yeah.
NLP is really what lets AI interface with us using our most fundamental human communication tool, language.
It's absolutely about building that bridge of understanding, trying to connect the richness and ambiguity of human expression with the precision of computational processing. It's a huge ongoing challenge.
Wow. We have covered a tremendous amount of ground today, really truly diving deep into these fundamental concepts that underpin artificial intelligence and drawing our insights directly from these foundational source materials we had.
We really have. We've looked at what it means for an agent to be rational, focused on achieving optimal outcomes, and how it strives for autonomy by learning from its own experiences rather than just solely relying on its initial programming.
Yeah, and we explored how agents reasoned about the world using logic and different kinds of knowledge representation formalisms. We saw how they build these internal maps of understanding and make deductions based on perceptions, using examples like the Wumpus world and grappling with core properties like monotonicity and logic.
We also discussed how AI has to handle the unavoidable uncertainty of the real world, leveraging probabilistic methods like Bayesian networks, assessing the value of gathering more information before acting, and ultimately aiming to find these optimal policies for navigating complex stochastic environments over time.
And then we really delved into how agents perceive the complex environment through all sorts of sensors, with a pretty deep focus on the challenges and techniques in computer vision. Everything from understanding basic image formation and illumination effects to extracting meaningful features, trying to reconstruct the 3D scene from multiple cues, and recognizing objects despite all that immense variability in appearance.
Right. And finally, we touched on natural language processing. Understanding how AI identifies human languages, how it processes text using statistical models from those simple character trigrams, and the surprisingly powerful bag-of-words approach for tasks like information retrieval, all the way to more complex methods for information extraction that need some grasp of syntax and semantics.
It's really been a journey through the core capabilities required for what we think of as intelligent behavior, perceiving the world, reasoning about it, learning from interaction, and deciding how to act effectively, all built upon this fundamental framework of representing knowledge somehow.
And all illuminated, hopefully, by the foundational principles laid out in that source material you shared. It really covers the building blocks.
It does. So reflecting on this huge, diverse range of approaches we've discussed today, everything from formal logic and precisely defined policies to probabilistic reasoning under uncertainty, statistical learning from just vast amounts of data, and these complex multi-cue systems for perception and language. And what do you think, based on all this, is maybe the single biggest remaining challenge in creating truly intelligent and broadly capable agents? Is it perhaps the fundamental limitation of representing the sheer complexity of human knowledge accurately? Is the need for more robust and generalizable learning algorithms, ones that can adapt faster with less data? Or maybe it's the difficulty of finding a truly unified architecture, something that seamlessly integrates all these different capabilities: logic, probability, perception, language, allowing an agent to reason and learn in a truly holistic way. Based on everything we've covered today from the sources, what stands out to you as the most significant frontier ahead?